Let's say there's a rusty bolt right there, okay? And you're going to use a wrench to crank it out, okay? So we put the wrench around it. Let's use a blue wrench, shall we? We put a wrench around it like that. And then we are going to apply force, right? Okay, most people who are smart will apply the force in that direction, right? But say somebody's not that smart, okay? So this not so smart person is applying the force in this direction. Let's say this force is being applied in that weird direction. I always never draw this thing high enough. Okay, there. You know what I'm saying? Okay, and then some of these force is being wasted, as you can see. This is force vector. Okay, now we can split this force into two components then. One of them is in this component, right? And if this angle right here is theta, and this is x component as we know it, right? F cosine theta. And then the other component is this one right here. And this will be f sine theta. So far so good? Now, but this is that way, right? Because it's a rusty bolt, it only wants to rotate. So that only force that is exerting, and we call that torque in physics. Torque is the twisting power to crank this thing out, is in that direction, isn't it? All of that is being wasted. So that's number one. So this is the only component of the force. The other thing is leverage. You know that if you're holding this part of the wrench, then it's not that smart, right? You want to hold it as far as possible. This is called the lever. And you want to, length of the lever matters, right? If the lever is twice as long, then you can exert twice as much torque. Did you know that? Hence the term leverage. You get it? So this length matters quite a bit too. Okay, so I'm going to draw a vector in there. So that vector, we'll call it R, goes from here to here. How's that? Okay. And let's put that in what color? Let's put it in blue color. Okay. So this is vector R right here. Okay. So this thing called the torque in physics, and since T is used for time and many other things, temperature, we'll call it tau, Greek letter tau for torque. Magnitude-wise, it depends on the length of the lever and F sine theta. Good? So this is a magnitude of the torque. Now, and of course, mathematicians being who they are, they want to make vector out of it. And this is known as the cross product. R cross. It's R cross F. It's not F cross R, because as you learned from pre-calc, if you switch these things, you don't get the same vector, right? So this is non-commutative, the vector multiplication. Okay, and then the end result here is a vector. Okay, so let's look at what this thing looks like then, eh? So if you have 3D space, and this is a nice picture to draw. So if you have 3D space here, I'm gonna use that one. Oh, not like that, but hey, I can recycle that vector. Say if we have one vector like this, and we have another vector, let's say like that, okay, in two different directions. Then if you cross the two, what is the resulting vector? Resulting vector will be perpendicular to both of these. Okay, so let me write this down. So if this is a vector R, and this is vector f. Okay, I'm going to move my r out over there because I'm going to throw something. And then r cross f is this one. And it has to be perpendicular to this and perpendicular to this. And this angle is what we call theta, which may or may not be perpendicular. Okay? And generally, there's no reason for this to be perpendicular. Okay? Now, then, what is the magnitude of this? And magnitude of this, of course, is here RF sine theta. But do you remember from pre-calc, if you find the area of this parallelogram, this area happens to be RF sine theta. That's the area of a parallelogram now, isn't it? So this is a good picture. Okay, and then we use something called the right-hand rule. So it depends on that way. So can you see my hand? Okay, you extend your hand out towards the first vector, which is r cross f this time. And then you bend your finger towards f, the second vector, because your fingers don't really hyperextend to the other side that much. You know what I'm saying? And then direction of your thumb is your cross product. So if you put r, f this way, and then cross product is upward. However, if you put r, f that way, r, whoop, it hurts, right? Then you have to, right, bend it that way, and then cross product is downward. And the length of this cross product vector right here happens to be same as the area of this parallelogram. How's that? Okay, so that's physically what it looks like. However, your pre-calc teacher taught you vectors like this. If we have r vector, let's do it black. If you have r vectors, which is, I'm going to call it just x, y, and z, and then f vector, which I call it fx, fy, f sub z, like that. And then cross product is given by this, r cross f, then given by the determinant of I, j, k unit vectors. Remember this, or remember forgetting this? And then we put the first vector, this order matters, x, y, z, which is r, first r cross f, so r goes here and f goes here. fx, fy, and fz. How about that? Okay, let's compute this. So if we compute this, then we do like this. I, j, k, remember, and this is a minus 1, right? Do you remember the sign chart? Plus, minus, plus? Okay. And then for I, you cross this out, right? You want me to draw these things, what to cross it out? We're crossing this out for I and take a cross product. So it's this minus this, right? Determinant. So we have y fc minus, ooh, not enough space, right? I'm gonna shove that thing away. So y fc minus c fy. It belongs to I vector. Good? With me? And then we have that minus sign, which I'm gonna write right here, minus, and then let's erase these two lines. And then j vector is crossing this out like that, right? So it's this minus this. So x fc minus this one, z fx. So far so good? Say yes. Say something. Feel free to use your microphone once in a while, children.
Yes.
Okay, see, when was that so hard? And what I do is, instead of a negative sign and this minus this, many times I do this minus that. Whatever, it's the same thing, right? Okay, and finally, k vector is this. So it's this minus this. So x fy minus y fx. Okay, that's the magnitude of cross, that is the vector cross product. Okay. Well, what we have to show is this thing really same as RF sine theta, then? Let's do that. Okay, it's going to get very ugly, so hold on, okay? So first, I'm gonna figure out the magnitude of this. Okay. Well, it is just each of these individual thingies square now, isn't it? So what we have is y fc minus c fy squared plus x fc minus z fx squared plus x fy minus y fx squared. That is where this magnitude square. Are we good so far? Okay. Then, yeah, there's no easy way about it. We're squaring it. Okay. So follow me carefully. This is y squared fc squared minus 2yz f, alphabetizing it in order to compare it later, plus z squared fy squared. Too much algebra? I'm going to go down in order to organize it. So second one is x squared fc squared minus x2 xc fx fc. With me so far? Z squared fx squared. Too much algebra? Okay. And then plus the last thingy is x squared f, that's y, right? Y squared minus 2xy fx fy plus, there's a pattern, y squared fx squared. So that's that thingy. Okay, now I'm going to have to figure out this thingy, rf sine theta, and I'm going to square that. Okay, that of course is r squared f squared, and then sine squared, which is 1 minus cosine squared theta. You with me? Okay, and that is of course equal to r squared f squared distributed, so r squared f squared cosine squared theta. Still with me? Okay, now that of course is equal to r squared f squared, that stays the same, but this thingy, where have we seen that pattern before? rf cosine theta. That is our dot product now, isn't it? So dot product is of course r dot f squared. Say yes. Okay, now the hard work begins. So r squared is this, right? X, Y, Z. Who's lost? Vector magnitude is square root distance formula looking thingy. And then that times fx squared plus fy squared plus fz squared, right? And yes, we are going to multiply that out. And when you thought that was awful, oh, wait for it. Minus, what is the dot product? Is it fx plus y fy plus z fc? That's a dot product, and we square it. Oh my god. Oh my god, right? Okay. Shall we get to it? Yeah. So the first thing, we have to do this thing systematically. So I'm going to distribute with x squared over there. So we have x squared fx squared plus x squared fy squared plus x squared fc squared. You with me? And then I'm going to go down and kind of like matrix idea, y squared, distributing y throughout, fx squared plus y squared, Fy squared plus y squared Fz squared. Still with me? And plus distributing z squared fx squared plus z squared fy squared plus z squared fz. Once you organize it, then these are not that bad. Okay, now I'm going to distribute this thing to itself, so, and then minus, so everything here will be minus x squared fx squared plus x y fx fy, you get it? Minus xc fx fc. That's distributing this term to all three of these. Now distributing the middle term to all three of this will be minus xy fx fy plus or minus, oh my god, that one is minus as well, and then y squared fy squared minus c fy fc. Okay, then lastly distributing that term to all three of them, so we have xc fx fc minus yz fy fc, and then minus lastly z squared fc squared. Whew. That was a lot of work. How are we doing so far? Are we good? Okay, then let's cancel a few things out, shall we? Okay, you see this thingy cancels that thingy, right? And this thingy cancels that thingy. And this thingy cancels that thingy. You with me? Okay, now let's start comparing. I'm going to zoom out and we can compare. Okay, let's see. Y, F, that thingy. I did not want to do it that way. What is that thing? Y, I cannot read my handwriting. That's Y, right? This thing is Y right there. I believe, yes. Okay. Y squared Fy squared. Y squared Fy squared is right here, right? Good. Okay. X squared Fc squared. X squared Fc squared is right here. Good. And then x squared Fy squared. So x squared Fy squared is right there. So those three are all matching. Good. Say yes. Okay. I'm gonna do the last term first because that's like, yeah. Z squared Fy squared. Z squared Fy squared is here. Z squared Fx squared here. Y squared Fx squared here. So far so good. So at least I got this column, which is all here. So far so good. Now let's see what's left. I'm going to go with the highlighter now. This one. Negative YZ Fy Fc. Okay, now YZ, here's one of them, and then here's another one, so there are two of them. Good, right? Okay. And then I'm going to look at this one, XC term. I believe this is one of them, and then this is another one. Ah, okay, so we have only one left, but only one, since that's the one left. Do you see that thingy here and here? Ah, we have an exact match. How about that, eh? So now we can say, therefore, it's been proven that magnitude of two vector cross product is same as magnitude. To emphasize it's a magnitude, I'm going to write it like that. Magnitude of each times sine of the angle in between. Okay. Any question before I give you an application? Okay, well then. Application here is, how can we find the area of space triangle or space parallelogram? So we have a force going that way, right? And then of course, when I said red color, it shows up in blue. And then we used to be able to figure out the component and projection, right? So suppose like x component or a component, say this is the direction of a vector. So this is a vector. And this is f vector. And then remember, we wanted to figure out this a component, that much, right? Okay, so that thingy looks like this. That much. I'm gonna put it in blue. So this is f cosine theta. And you still remember this was component, a component of f. And let's go through the whole thing and figure out, because this is very important. This is AF cosine theta over A. So we get A dot F over A. You get it? You still remember this? Component, X component, if you will. Okay. Now, whether you want this as an absolute value or not is a judgment call, right? In the notes, I put absolute value. Do you want this as a magnitude only, or do you want that positive negativity? And this time I just decided, yeah, magnitude only, right? That is a judgment call. Depends on how you want to do this, right? Okay, but what about this y component, or known as orthogonal component? One of the homework problem was, well, we can do this f minus this projection, right? Well, that's pain in the butt to calculate. So could there have been a better way to calculate this? Well, before we didn't know what cross product is, so we didn't know, but now we could do it. This component, right? Okay, let's think about it. This component right here is orthogonal component. Ortho. Was it ortho or ortho? I forget.
It was
Orth, A, F, like that, right? Okay, and if this is still a magnitude, it's a scalar, and that of course is F sine theta, isn't it? So far so good? Right, why do you get, what's the meaning of that facial expression? This is cosine and this is sine, right? Tell me, still remember trig. Now, but if I write it like this, AF sine theta over A. Wait, does that numerator, and this is definitely positive, let's just make sure, right? This is positive, but A, right? Does that numerator trigger some memory? Yeah, that's a cross product, isn't it? You get it? And that's one convenient, and later this becomes a big, big deal. This is how you figure out the orthogonal component or y component. Because later, when we are dealing with accelerations, in fact, why don't I talk about it? Little brief intro for the future, okay? Suppose path of a particle in 3D looks like that. So this is my R vector, okay? And then what does the velocity vector look like at a point? Let's say at this point. Velocity vector, of course, is a tangent. Do you believe it? To the curve? Let's say this is a velocity vector. Okay, that doesn't look like tangent, so I'm going to force it to be tangent. that point. You know what I'm saying? So this is velocity vector. So far, so good. Now, suppose you're driving, right? And you're not only driving, going into the curb, but you're stepping on it and drifting and all. Where does the acceleration vector point to, is our question. Have your physics teacher taught you the centripetal acceleration so far? Okay. Centripetal acceleration will always be perpendicular to this. It's inward like this, isn't it? This is your centripetal acceleration right there. However, you could have more than just centripetal acceleration. What happens if you're stepping on it and accelerating and then turning at the same time? Then you also have a linear acceleration, or tangential acceleration, they call it. So let's say that thing still coincide with this, right? So you're kind of like speeding up and turning into the corner. So far, so good. So this is centripetal acceleration, and this is linear or tangential acceleration. And then real direction of the acceleration vector happens to be vector sum of these two. What color should we have this? Green? I'm generally not a fan of green color, but hey, green it is. Okay, this is acceleration vector. You get it? Now, here's the significance. As an engineer and scientist, we basically measure this component and this component, right? This is how much you're giving it to the engine, throttle or gas. And this is how much you turn, and then your tire friction provides this, right? However, mathematically, if you take second derivative, it gives you this vector. Which means once you have this vector, we have to do components. How are you gonna do that? Well, that's where this thing comes in mighty handy, these two things. One of them, this in our picture is tangential component, and this is your centripetal component of the acceleration. You know what I'm saying? So later, this will be biggie and possibly part of the take-home exam. You have to know how to split two vectors according to tangent to any vector and orthogonal to that vector. Comes in a big time. Any question? Okay. Other little application of this is find the area of space parallelogram. Okay, that one, I think I'll just copy the picture from the note. It's like easy enough for you to understand. Okay. Say, this time I just did it in 2D to enhance the understanding, but it's really done in 3D. And then area of a triangle is half of that parallelogram. So suppose we have this space parallelogram. In this case, just 2D. So Z component is 0. Okay, then let's just consider this. All you need is like vertices, right? 0, 0, 4, 0, 3, 4. But it could be any three-dimensional, right? All you have to do is calculate two vectors on the adjacent edge. So this is a vector and that's a v vector. And so in this case, it's 4, 0 and 3, 4 to make it for the simplicity of the problem. And then, do you agree that area of this parallelogram is the space times height? And then do you also agree this height is b magnitude sine theta? So if you multiply it, it's AB sine theta, and this was one of the formulas in your pre-calc book now, wasn't it? But then AB sine theta, I mean, that's definitely cross product now, isn't it, right? So if you take cross product of this, surely enough, you get 16, and which is exactly the area of this parallelogram. But suppose you're given 3 coordinate points of a space triangle. You can still find this vector, you can find that vector, cross the 2, divide that by 2, and magnitude divide by 2, then you can find the area of the space triangle too. they are not necessarily on like XYZ plane or anything like that. So these are just 3 random vectors. So I'm gonna give a coordinate. This vector A that you see up there, I'm gonna say that is A sub X, A sub Y, and A sub Z. How about that? Okay, just any 3 D vectors. And then vector B here is Bx, By, and Bz. And of course, C vector is Cx, Cy, and Cz. So far with me? Let's calculate the volume of this thing. Okay? So volume of any prism or anything is base area. Oh, that is a weird base. Base area times height. Remember that? Okay, and then we can use anything as a base, but the picture is lined up like this. So that is that parallelogram. These are all parallelograms. So let's call that base. This is your base area, base. And then height is that perpendicular to that base. You know what I'm saying? You see the picture? Okay, so what is the base area so far? Do you see that base area has to be this magnitude of B vector, which is B, magnitude of C vector, and then sine of that angle in between, which I'm calling it B? Do you agree that this is how you find the area of a parallelogram? Or you want me to derive that for you? I could totally. If you need me to figure that out, area of parallelogram, now is the time. Y'all got it? You know this much? Okay. And then times, let's figure out this height. Okay, let's just write it h at the moment. And then we can see h. Is that A magnitude times cosine of theta? Say yes. You want me to figure that out for you? Or okay. So we can replace this with A and then cosine theta. You with me? Okay. Now, what is BC sine phi? Does that remind you of this is a cross product? It's magnitude, because cross product itself is a vector, so it's a magnitude of cross product. That was the proof last time, eh? And then this, let's just think about it. This is a vector, right? Let me just write it like this, A cosine. This is a vector magnitude. This is a vector magnitude. So magnitude, magnitude, cosine. Does that also remind you of a dot product then? Yeah, so this is really cross product B and C dotted with A. Well, I can move it around. Oh, yeah, here's a weird question. If I don't put parentheses like this, because like this is what I really, now it's exactly the same thing. But let's suppose, for the sake of this argument, let's say I did not put parentheses. Then order of the operation, which one has a higher precedence? Dot product or cross product? Because in algebra 1, you know, multiplication is the exact same, right? So you have to start from the left and move to the right, right? But then this ain't algebra 1, right? So which one has a higher precedence? Dot product or cross product? They are not the same multiplication. And if you apply a little bit of logic, that answer is there by looking at it.
Cross product.
Cross product. Why cross product?
Because if you do the dot product first, you're going to get a scalar cross a vector.
Oh, excellent. Do you all see that? Suppose we do the dot product first like this, right? Once you take a dot product, it becomes a scalar. And you cannot cross the scalar with a vector. You know what I'm saying? So cross product always goes first, even if there's no parenthesis, okay? Most people put parentheses here anyway way because it looks better and it's like takes out the ambiguity, but you should know, right? This is okay. Now we are going to take this dot product, cross product. Okay? Okay, let's go. So I'm gonna here. A vector is AX, oh no, right? AY and AC, AZ, AZ. AZ. Dotted with cross product. Do you remember cross product was done like this? And then BX, BY, BZ, and then CX, CY, and CZ. Do you agree this much? Okay. Now let's just think about it. This thingy gives you I vector with this determinant, and this thingy gives you J vector, negative J vector with this determinant, and this is K vector with that determinant, isn't it? And I'm dotting this with this is a I, J, K component. So why don't I just put them right here? You get it? So this thing turns out to be AX, AY, AZ, BX, BY, BZ, CX, CY, and CZ, which is known as triple scalar product. And that gives you scalar. How about that? Positive y-axis, let's say we have a red wrench, right? So this, I'm going to call it R, either for wrench or radius. Oh, conveniently works out, right? And this will be 0 and 30. And no, we cannot do 30. Do you know why? It has to be 0.3. Why is that? Somebody tell me why this is 0.3, not 30.
Because it was in centimeters.
Centimeters, joule in, remember, Newton meter is joule. You don't take physics. Okay, if you take physics, Newton meter. So this is metric. It has to be in meters. So 0.3. That's our R, right? Now we apply the force and a direction of 0, 3, 4. Okay, 0, 3, negative 4. So it's like somewhere down there, right? I'm going to move this over so I can draw that vector. So we'll apply the force. And 3, negative 4, so it should look like this. And let me make that a blue. So far, so good? Now we have to take the, so this is our force right here. F is equal to 0, 3, negative 4. Now we have to find the magnitude of the torque, right? Okay. Oh, this is not the force. This is just the direction, huh? You notice that find the magnitude of the force needed to supply 100 joule. You know what I'm saying? So this is not quite F yet. Well, how can we do this? Well, very cleverly, I'm going to put some kind of constant in front because this is just giving me the direction. You get it? So what should we call this constant? Sarah, give me your letter. And don't say S.
C.
C. Okay, so we'll put some kind of constant C because we don't know the magnitude of this force, right? At the moment, it appears that magnitude is 5, right? And those of you who really want to be anal, you can actually make this a unit vector and then like 3 over 5, negative 4 over 5, you can do that. Then whatever this becomes the magnitude of your force, right? But we can just take the magnitude of this whole thing. I will let you decide which way do you want to do it. Do you want to make this thing unit vector and divide both by 5, or do we just want to do it and then find the magnitude that way? There's a trade-off. Like depends on how much you love fractions. Sarah, your question, your decision.
I guess let's do it the unit vector way.
Unit vector way. Okay, so and then this is 3/5. You do understand, all of you, why this unit vector way you have to divide by the magnitude, right? If you use distance formula or super Pythagorean theorem, this thing becomes 1. Then this is our magnitude. Oh, in that case, I'm not going to call it C, I'm going to call it F magnitude, right? Magnitude and the direction. And later we are going to get into this a lot. So far, so good? Okay, so let's calculate the torque. Torque here is, of course, I'm gonna write down R cross F, right? Which happens to be I, J, K, and then 0, and let's say 3/10. I'm regretting this already. 0, and here 0, 3/5, and -4/5. You with me? Okay, let's compute this. So you cross this out, and then you have this. What is this? -12/50, right? I'm really regretting this fraction decision now. And J, this is a -1. Oh, luckily that's 0. Thank God, right? And K, oh, that's 0. Wow, we get away with 1, right? Do you know why this is happening? Because this is in YZ plane, and if you cross the 2, it has to be perpendicular to both of these vectors, which means it's got to be in some kind of x direction or negative x direction. You get it? Right. Oh, I forgot one thing. I forgot that F, right? It's really F. So why don't I just put F out here? Common factor F. Good? Say yes. So I have to put common factor out here. You with me? Now the magnitude of this torque needs to be, what was it, 300? 100. This needs to be 100 joule. Why am I using? Okay, torque, those of you taking physics, it's got to be Newton meter. I know Newton meter is same as joule, but when we talk about energy or work, we say joule. But when we talk about torque, physicists never say joule, it's Newton, because they are two different concepts. They happen to have a same unit, okay? So it's Newton meter. Meaning, what we have is 12, magnitude of this is just 12/50 times F, which is equal to 100, right? That tells you what F is. F is 6 Newton. Get it? Oh, that was pretty clever problem. I like it. I like it a lot. How come nobody ever asked that question before? Is that it?